that is recorded on exams will be December 22nd in Ravenna 11, and the next date is January 12, Ravenna at 11, and the next is January 28th, is a Wednesday, Ravenna 11, and we can also schedule another date in February if needed. So this is recorded. I also asked Serena to send a message on the chat, and the forum. Sorry for that. Second thing, I think you are the only one interested here, but lab, we can make the same dates, okay? So for the laboratory, same dates, and you can also make both of them in one day, no problem. And then for the lab, I will also tell you some instructions on how to make it, but I already said something at the start, the first lecture for the lab, and there is also a summary written on the web, on my website. Second thing, for the lab, there is a lecture next Thursday for the lab, I mean, and I am delivering the lecture online, okay? Yeah, online. And I think you have also another one with Ray, or Ray, did he finish? I look at you because I think he gave 2 or 3, I don't remember. Anyway, 3 already? Okay, perfect. So the next Thursday will be the last lecture of the lab, okay? And again, it will be online, and because last Thursday nobody was here. And did you mean to come here in presence next Thursday or not? No. But anyway, I think it's better if we make it online, okay? Because also you have to make some exercises. It's better if we make them online, okay? I will send a message on the forum because there are also other students who may attend online, and that's it. Okay, so yeah, no problem. It's recorded and it's available from now because I uploaded the video just now. And also I uploaded the videos of last week's lecture just yesterday night. So everything should be updated now in terms of videos. Okay, very good. Now let's go here. And we finished with climate models. So now you know. Let me just check if we finished. I think I asked you a confirmation, and I think no, I think we didn't finish. Okay, and this is good. This is correct. So let me just check very briefly where we. Sorry for that. Where we got. Just 1 second. Yeah. Okay, let me just, I can show you the PowerPoint and then you tell me. Okay, just 1 second. So I open it. And it's here. Okay. So I think, oops. I think we got here. We got to this one, the boxes. I think we discussed here. Please stop me. You said 19. Yeah, the last part was the RCP. Ah, okay, okay. Yeah. Okay, so just check RCP. Yeah. Yeah, it's here. Let me just check. And 1 second. Okay, good. So the RCP, correct? So I think we got here. No, not here. This one probably was. Okay, very good. Okay, basically we finished anyway, but I just would like to start from here because I want to just summarize what is the purpose here. The purpose is that you gain an understanding of how future climate scenarios may be generated, and one possibility is to use climate model is by far the most used. And so basically climate models, you already have an idea of the structure. They are gridded models which work on elementary volumes by applying conservation equations. And we talked about the transport theorem, Reynolds transport theorem, which is the basis for conservation equations. So be sure that you remember the concept, conservation equation, and you remember the concept of the transport theorem. I told you that it's not necessary that you remember the full demonstration of it. And but it's also important that you remember what are the input data and the initial and boundary conditions, and in particular the emission scenarios, which depend on future development, and they can be estimated according to different hypotheses of future development. So there is the business as usual, which is the more pessimistic, and then there are other scenarios which are more optimistic, and they are based on different hypotheses on the date on which we will reach the cap of emissions. Cap means the top of human emissions. And we said that according to some studies, it seems that we are not very far from it, because indeed there's been a decrease, or let's say a decrease of the increasing trend in human emission due to policy making and due to then climate change mitigation, policies for climate change mitigation. Remember, reducing the human emissions is the most important strategy for climate change mitigation. There are other strategies for climate change mitigation, which are based on carbon storage, for instance, in the underground. So they are essentially based on reducing the concentration of CO2 in the atmosphere by increasing the Earth storage rather than decreasing human emissions. But for sure, the most important strategy to climate change mitigation is, as I said, the reduction of human emissions. Okay, now after that, I said that we don't discuss about uncertainty because we already discussed it. But the important thing is that you have to be aware, and now you have also an understanding of the reasons for that. You have to be aware that the predictions by climate models are uncertain, and this is particularly important, as we discussed, in the field of engineering, because in engineering we have to at least know what is the magnitude of uncertainty. Once that we know uncertainty, it's not a problem. We are used, we know how to make design projects under uncertainty. But of course, we have to at least have an estimate of it. And we already discussed that this is still an open question in climate science. Indeed, we know that climate models are uncertain. We know that uncertainty is variable in space and time. It depends on the region, it depends on the local context, but actually we don't have still a quantitative assessment of uncertainty that can be considered reliable for engineering applications. So you may have, if you read the literature, if you read the literature, there are several interpretations of uncertainty of climate models. But beware, these interpretations are based on assumptions that basically neglect some causes, drivers of uncertainty. And therefore, when you turn to engineering, these estimates are not useful. And so I say it again, I confirm that for the purpose of engineering applications, how to estimate uncertainty of climate models is still an open question. There are several research projects that are working on it. And my opinion is that these estimates of uncertainty should be obtained by comparing and there is written somewhere here, and probably also in the PowerPoint, let me check. As I said, estimate of uncertainties should be obtained by comparing historical simulations of climate models with corresponding observed variables slash statistics. Okay, it depends on the indicator of climate change that you choose. If your indicator of climate change is a change in the average or standard deviation of extreme rainfall, then you compare historical simulation of average standard deviation of extreme rainfall on a given time window with the corresponding statistics computed on historical data. This is my interpretation, and beware that this interpretation is not always accepted by the climate community because it leads to relevant uncertainty. It leads to relevant estimates because if we compare historical simulation, they are available on the web of climate models with the corresponding statistics of observed data. They are available on the web. You see that indeed there is a large uncertainty. And of course, this large uncertainty is in a way not fully accepted by the modelers, the people who work on them, because they believe that when it turns to future predictions, the model will be more reliable. Actually, you know that with future predictions, you have also additional sources of uncertainty, like human emissions, as we already discussed. And so this is basically what you see here, and it's in the slides. And you see that there is, again, a recap of what are the reasons for uncertainty. We discussed them already. And you see that here, model testing includes adjusting model equation, and basically is what I said. So models that do not reproduce well historical climate scenarios, which means uncertain, can be adjusted by correcting their simulation to match selected statistics of the observed climate. Of course, it's not an easy task for an engineer to adjust models. Usually we, as engineers, we use model outputs, which are available on the web, and you know how to retrieve them. Of course, adjusting these predictions is not really an easy task. However, for your information, beware that there are several examples of engineering applications that require the fit for purpose future climate scenarios. And these engineering applications have been carried out by running independently by the engineer a climate model. So I give you an example. The Italian company Ferrovie dello Stato, who is managing the national railways, they needed a climate simulation to check if a section of the railway line was exposed to floods, and they wanted to make a fit-for-purpose simulation. So what they did, because they wanted a model with very high resolution, what they did, they took the boundary condition for the model, they set up their model, and ran indeed the climate simulation. So this is an example to let you know that indeed in this field, climate change adaptation, we already have the tools also for producing in-house these climate simulations. And I also did that because I was curious when I knew that they could do it on a personal PC. I indeed tried to do that, and I was successful. It can be done on a personal PC. Of course, you can run on a personal PC only the model for a small portion of the land. So, for instance, I ran it on a portion of the Emilia-Romagna region, a limited one, with a resolution of 3 kilometers, but indeed I was able to do that. And it's really not difficult. Of course, you need a personal computer that is a bit powerful, possibly under Linux, because all of these models, they are available on the web. You don't just have to download them and learn how to run the model. You don't need to really modify the model. If you want to modify it, you can do it. But of course, to modify, because it's open source. But of course, to modify a model requires additional knowledge. But what I did was to get a model that was already done. I downloaded it and I ran on my PC and I changed the boundary conditions. And as I said, better on Linux, because for Linux there are plenty of instructions. For Windows, I did not try, but I could see that the instructions are, they advise to use Linux because of computational efficiency. Of course, if you run it on a personal PC and the personal PC is already working under stress by the operating system, it becomes a bit of a problem. And of course, you cannot bypass the problem by building a virtual machine under Windows, of course, because the virtual machine is an additional charge. You should run it on a Linux PC. By the way, with the laboratory, we are trying with a virtual machine to run some Linux simulation. And this is just to show you that Linux is very easy. It's not really a problem. And keep in mind that if you're interested in your PC, you can put a dual boot. Dual boot means that you choose when you turn on the machine, whether to boot it on Windows or Linux. And this is something that is easy to be done. In several of my PCs, I used this solution. Okay, so let's go back to uncertainty. So you now have a full picture of an alternative that is possible to choose in order to make a design project under climate change. So you need a design variable for the future, you run a climate model. Let me see, here there is an example which is related to uncertainty, which I think is interesting that I think we already discussed about it, but let me make a recap. Usually, when you read reports from uncertainty of climate model predictions, they present uncertainty in the form of ensemble simulation. This is widely used, widely used. So they use different models, different initial conditions, different forcings, and produce several predictions of future climate. And then you obtain something like in this figure. This is very simple because you have only 3 models. But usually people use like at least 20 models with several initial conditions. And indeed, you can find in the climate data store of Copernicus future runs by several different models with several different initial conditions. So you can put together like 100 simulations very easily. And usually this report, like the IPCC, they present the envelope of the simulations as an estimate of uncertainty. Beware, this is a classic example of an underlying assumption. And the underlying assumption is that precisely the ensemble is representative of the uncertainty of your predictions. Yes, basically, if you take the envelope of several ensemble simulations and you assume that the envelope is an estimate of uncertainty, there is an underlying assumption. The assumption is, to put it very simple, is that the envelope is representative of the uncertainty of the prediction. But let me make you, to give you an example that is contradicting this assumption. What if all the models are wrong? This is the question that sometimes I ask at conferences, like, okay, this is a very nice ensemble. You use different models, but what if all of them are wrong? And, it's possible. It's possible that the 20 models, they make 20 different predictions with different initial conditions, but the true value is outside of the envelope. It's possible. There is no demonstration that the envelope is encompassing all the sources of uncertainty. There is no demonstration. You may also see some attempts to weight the response of different models, basing on assign weights. Because of course, if you take the envelope, let me just make a sketch, just to summarize what I mean. One second. We always need to struggle a little bit. Okay, so let me pin the blackboard. I hope I forget to unpin it. I remember to unpin it. Okay. So let's suppose that you have a climate variable. I call it just y, okay? And depending on time, yt, okay? And then you have a forecast time, so the time at the present time here, t star. And you start, and here you have, of course, an observed value, because it's now, and then from now we have this situation. Okay, fine. So we get one model and we get this trajectory, for instance. Like, if you remember the figure that was there previously, let me put it back. So you get one trajectory, for instance, the red one, very good. And then you take another model and you get a second trajectory, which may be like this. And then another model, which can be like this one, like this figure, okay? And you get several predictions. Okay, let's suppose that this is the time that I'm interested in, the double star, and I want to predict the value here. What is the true value? So you have several different predictions. There is a possibility that you take this envelope and you estimate a probability distribution. Okay? And then you take the average of this probability distribution. And for instance, it's there. Okay, this is a way of combining the models, and what you are doing here is to assume that the models are equally likely. Okay, and then, I mean, it may happen that the prediction is this one, it may happen that it's this one, and where they are more dense, then you get a probability distribution, you estimate the probability distribution. But you may also have some information, and this means that you are weighting the model simulation to, for instance, remove one simulation. So maybe that you have an additional simulation that, okay, this is something that I remove. Or your information may advise you that this output is very unlikely. Removal means impossible, but maybe it's very unlikely. This means that when you compute your probability distribution over the data, you give to this simulation a very low weight. So you either don't consider it, so you exclude it from the estimation of the probability distribution, or you give to it a very low weight. Here, basically, they count, in this example, they count, every simulation counts one, like one is here, one is here, one is here, one is here, and one is here. And then when I estimate the probability distribution, I just compute the frequency by counting each simulation as one. Okay? But if I count the simulation as 0.1, when I estimate the frequency, of course, the value is given a lower weight. So when you compute the frequency, you say, okay, this doesn't count for 1, but as 0.1. And this weight can be computed in different ways. Usually people give, they can be subjective. Like people may say, okay, let me say that this one is very unlikely, because they have some information that is like Bayesian. okay, based on perception. Or they may have some additional information like this model was indeed validated, was tested, and it turned out to be less performing, like with a quantitative measure. It was estimated to be half performing with respect to another model. So you give a likelihood of half of the likelihood of the other model. It depends on the purpose of the application, and the literature proposes different ways of weighting. But even if it is weighted, you have to be aware of the fact that in any case, the ensemble is based on some assumptions. And as I said, simply speaking, the assumption is that the probability distribution that at the end of the story you estimate is indeed the probability distribution of the true value, the value that you will observe. But what if, again, the question that I often ask at conferences when I want to contribute to the debate, what if all of these models are wrong? So the true value may be somewhere right here, true. Okay. So, again, in my opinion, the only way to estimate the distribution of the prediction is to make this exercise not for future prediction, but before then moving to the future prediction, I need to perform an historical simulation. And therefore, I can really estimate when, under which condition the models worked well, under which condition this probability distribution includes, gives a correct probability of value, and in what conditions instead it fails. And then I may correct the model as I wrote in the slides, like, okay, these models in the historical simulation produced a very poor picture. Let me correct the models. By the way, there is a study which I stumbled in, which did this exercise. It was a paper published, I think, in 2015 by a very relevant research group. And they adjusted the models based on historical simulation. This was an early attempt to try to adjust, calibrate climate models based on a comparison of their performances with observed data. What they realized is that after correction, the climate models were more optimistic about future changes. So they were less alarming in terms of response. And this is something that if you think at the whole story, at the global picture, it's understandable. So basically, when people set up a model and they don't have an easy way to test it, and the model is used to make a prediction of what may happen in the future if something goes wrong, a scientist tends to be conservative. So it was my expectation that after correction, the model became more optimistic after correction, because before the correction, if I don't have, again, an easy way to test it, I tend to be more conservative. And indeed, this research group demonstrated that this is indeed what happened, of course, with reference to a specific variable, a specific situation, and specific models. 10 years passed, but still the problem remains of the challenge, the open challenge of estimating uncertainty of future climate predictions. And as I said, as a guideline for you, just to keep an eye on the studies, the situation where the model is actually tested against observations. When you compute an ensemble here, the true way is not used. It's not used. I put it there just to tell you that it may fall outside, but usually when they make ensembles, try to check whether the models were tested against observations. This is something that should drive an engineer. Okay, this is the concept underlying engineering. Engineering relies on comparison with the reality. Scientific investigation is another thing. Also, scientific investigation should rely on comparison with the reality. What Galileo did in order to check if the trajectory of a body falling in the void was indeed represented by the equation, very known equation based on acceleration of gravity. What he did, he went over the top of the Pisa Tower. It is said that he went there and left falling some spheres of metal, of a very dense material, in order to make the assumption that the body was falling in the void more realistic. Because of course, if I release a sheet of paper, then the density is very low, and the assumption of null resistance of the air is not reliable. So he went there, and this is an example of the experimental method for scientific investigation. But in scientific investigation, sometimes it's true that we don't have the opportunity to make a test. Maybe the opportunity will come into the future, but we don't have this opportunity. And therefore, in climate science, it is quite normal and acceptable, reasonable that people sometimes work without testing. As I said at the beginning of this course, we cannot close this Gibraltar Strait in order to check what happens if the Mediterranean Sea remains isolated. So it is something understandable that we make assumptions, but for an engineer, and we don't test experimentally, but for an engineer, experimental testing is needed. And therefore, keep an eye on that. You see estimates of uncertainty, just look for testing with reality. If there is no testing with reality, you know that there is something that is not taken into account. There is some assumption that is not verified. Okay, and this is important that you get it, because very often you see estimate of uncertainty. If you look at the IPCC report, you see a lot of predictions with the so-called confidence band. We will define what is a confidence band today, okay? And these confidence bands are usually look for how they are estimated, okay? And they may be estimated on consensus, which is a Bayesian way of assigning weights to models, okay? Or they are estimated through ensemble with equal weights. Look for this information, okay? And in the IPCC report, as far as I know, you will not see testing based on comparison with experimental data, but there are several studies in the literature. Okay, good. And in any case, you can make the testing. I mean, for most of the cases, you can download a prediction and you have historical data, you can compare. Yeah.
For engineering, we need test.
Yes.
For science problems, we can make this step from the structure. I mean,
yeah. Yes, for the structural engineering, indeed, one way is to test in the lab. But with the climate, you cannot make a test in the lab. Or, I mean,
the others, of course, are subjected to uncertainty. We can emulate in the lab for the mission line, we take into account the data from the models and then we simulate it in the lab. Like, I don't know what was made in Japan really is in Europe would build buildings knowing what possible buildings can be destroyed.
Yes, of course, this is possible, but I mean, in order to understand what is the test that you have to make for your building, like, for instance, to resist to snow cover, you have to get some ideas of what will be the snow cover in the future, the snow load in the future. Let's forget for a while that snow load is predicted in the future to decrease, but we don't know that, okay? So you make predictions. And the predictions say that the snow load is going to decrease indeed under global warming. And you get an ensemble, okay, perfect. What kind of testing do you do if you don't have an estimate of uncertainty? So to what extent do you test your building to snow load increasing? So basically, these models, if you take the ensemble, any climate model will tell you that the snow load is going to decrease because they simulate warming. They are conceived for simulating warming. And therefore, if you put increasing emissions there, like we are required to do, because remember that the European Union suggests to use the RCP. Where is it? No, it's not here. The scenario that is most pessimistic, okay? And therefore you get an increase of temperature. Any model, any ensemble will tell you this is increasing temperature, but if you translate into snow load over a building, it's decreasing. Perfect. But should you, as an engineer, rely on the fact that the snow load is decreasing? At least I would tell it to an engineer, look, don't do that. I mean, the present situation is that snow load is like 400, I don't remember, kilograms per square meter. Don't take anything lower than that, because this is the current situation, it's the baseline. Otherwise, we have to admit that climate models may be wrong. You get an estimate of uncertainty, and you test a snow load of 500, but you need an indication, because otherwise you go in the lab and what kind of snow load do you take? Sorry? The worst, but you have all the models predicting that it will be lower than 400. What do you think?
In this case, the standard is being used at the point.
Yeah, but you will find no model predicting a temperature decrease and no model then predicting a snow load greater than today. So at least I would say to an engineer, take the snow load of today, okay? But still, I mean, temperature may decrease in the future. Why don't you exclude it? And but indeed, if you look at the predictions of climate models by accounting of uncertainty, and this account is based on comparison of past performances, you will get that the temperature is not necessarily increasing. And this is why it's difficult to accept such a response. So if you look at the performances of climate models to simulate the temperature change in the past, you get a very large envelope. And this large envelope, if you project it into the future, may include that temperature is decreasing. And then it would be correct to say, okay, let's suppose that temperature is decreasing with a low probability, but it may happen. And then I test with respect to a snow load that is greater than 400. But you have to get this estimate in some way. And this is why I'm telling you, do you trust the prediction of temperature increasing? Look at this model, how the performances were in the past. And then you get an idea of the errors. And look at the envelope, the resulting envelope. And so far, we didn't include the concept, we didn't introduce the concept of confidence level, confidence band. I will introduce it today. And you will better understand what I mean. Because the problem is that I have to get a prediction, and to estimate an envelope of uncertainty based on the confidence that I have of the model. And unfortunately, this envelope may include the no change prediction, or it can include the opposite change. So indeed, if we rely on climate models, we shouldn't exclude that global warming will stop. Okay, but climate models are only one option to estimate the future climate. Then there are other options, which I will introduce. Okay. So uncertainty. Here there are more details. And here there is another example of an example prediction. And you see here how many models? 3, 6, 8. Okay. This was issued in 2015, I think. And because you have to look at where the zero is crossed, because these predictions are expressed as anomalies, and from 1900 to 2100, but anomalies with respect to the global average at the time of prediction. So where you see that the zero line is crossed here, this is the date of the prediction. I think it was 2010, 2015, something like that. Now the situation is changed because they changed the emission scenarios, and so the situation is changed. But you see that indeed there is a huge, at that time, there was a huge difference between models. I mean, from +2 to +5, there are 3 degrees. It's really, I mean.
So the same shape of the recipe graph. We had done at the end of that one was negative. The because it was also negative graph or.
Yeah, the RCP is, I don't remember the meaning of this acronym, because the RCP, the emission scenarios were called with different acronyms as time passed, and they introduced a new one in the AR6 report. But here, I think it was business as usual. And I'm not sure I replied to your question. Did you ask what emission scenario?
I mean, last time we said I asked why in the graph for USP, the graph was also negative because it was
yeah, yeah, the reason is the same. Correct. Correct. Okay, and now, so what is the alternative then? The alternative to climate models is to use a data-driven model. What does it mean using a data-driven model? And let me just put the camera here and let me unpin the blackboard. Sorry. Okay. Okay. Now, what is a data-driven model? Here you see that it's called stochastic, but let's, for now, make a step back, because stochastic means statistics. And of course, a statistical model is data-driven, but there are many other data-driven models. Okay. And in particular, there is today widely used machine learning or artificial intelligence. Keep in mind that machine learning is just a branch of artificial intelligence. And artificial intelligence is a term that gained a lot of visibility in the past couple of years. But indeed, we were already dealing with artificial intelligence starting from the 90s, when a lot of computational facilities became available. And then today, artificial intelligence is used basically to identify ChatGPT, the chatbots, because they are actually a step forward of artificial intelligence. Artificial intelligence, anyway, includes machine learning. And what is a data-driven model? Is a model that looks at data and makes prediction based on the pattern exhibited by data, and then in the past. So you look at data means that you look at the past and you identify patterns. in the data. It's in different ways, but statistics is just a formalized way of looking at patterns. You look at patterns and then you extrapolate these patterns into the future, okay? And you may say, okay, but what is the rationale behind it? Because how can I make sure that the future is like the past? Okay, this is the limitation of the data-driven models. So especially in science, people say, we are talking about climate change. And therefore, if you look at the data are representative of something that is changed, is no more actual. So how can we use past patterns to infer, to understand, to predict future patterns? Look, first, the physical processes are not changed. I mean, conservation laws are not changed. What can change is the forcing, okay? Or boundary conditions, which is the same thing, I mean. But the physical processes that produced past data, they are not changed. They are the same process. So in principle, there is nothing wrong to use past patterns to predict the future. This is usual in engineering, is the traditional approach in engineering, and it's completely justified. Of course, if we think that the forces have changed, we have to account for it. So the data-driven models, which are the models that we traditionally use in engineering, they can still be applied, but we have to take into account of what is changed. So there is nothing wrong in doing that. And this is particularly important in view of the uncertainty of physically based models, of climate models. Because of course, if I had a model that is perfectly satisfactory, then I mean, it's an advantage. It's an advantage if I don't need data for making the prediction. It's an advantage because sometimes data are not available. And therefore, I mean, if I say again, if I have a model that is very satisfactory, tested, reliable, whatever, then it's justified that we, in a way, change our approach, leave our traditional approach for something that is becoming better. But this is not the case for climate predictions. The climate prediction, we have several demonstrations that still we are not there. And therefore, we don't have to leave our traditional approaches completely. We have to update them, maybe, but not leave them. Why I'm saying this? Because in many instances, you hear people, very qualified people, say the traditional approach in engineering must be abandoned, must be revised, must be whatever, and because it's no more reliable. But then my question is, what is the alternative? The alternative is to use climate models. We all know that it's not an alternative in itself as they are provided now. So it's not an alternative to go in the climate data store, download the future precipitation data over Bologna and use it to size a sewer system, because it may happen that the sizing is less conservative with respect to our traditional approach. This is why I said before earlier, don't do that. If you see something that produces an estimate that is less conservative with respect to the so-called traditional approaches don't do that. Okay, and so we cannot simply go to the climate data store, download precipitation to Bologna and use it. We have to at least make a comparison with our traditional approach. And let's forget about the lack of appeal of the word traditional. Traditional means that it has been used, tested several times, that is something that is accepted, and that's it. So, traditional is not necessarily wrong. It's traditional. It's usually it's true. It's fine. It's correct. Okay? And yeah.
Just to reinforce what Professor is saying, in my perspective, the reward that we gain from adopting a new result that we get, for example, in that case, it was mentioning that the temperature, maybe the load of snow will be decreasing, and then you do estimation on that data. The reward that you will get if you are right, yes, the reward that you will get if you are wrong are not comparable. So it's better to rely. Okay, I was wrong. Maybe it was now it's 300. I designed for 400, but okay, I'm safe. But what if I designed for 300 and unexpectedly in the future it increases to 500?
Yes, this is, we will discuss decision theory in the last two lectures. We will discuss decision theory. The question that you raised now is a typical question of decision theory. So, okay, I designed for 300, but what happens if something like 400 comes? And this is a typical question of decision theory. And decision theory, what it is suggested, just to give a very brief anticipation, for instance, is to use no-regret solutions. Like, I designed for 300. What happens if 400 comes? No big problem, or at least some minor damages to the structure, no risk for the life of people. So no regret. Okay, and that's fine. And we will discuss how to take decisions in the face of uncertainty in the next two lectures. Okay, and what you are mentioning, reward, is indeed an essential ingredient of decision theory. And decision theory is also very popular in gaming, in making investment in the stock market, and because sometimes you need to evaluate uncertainty in stock market predictions. They are very good in economics. They are very good in estimating uncertainty, and they also estimate what is the damage and the reward. Usually, when you take high risk, you may gain high reward, but also a very high damage. So you have to decide what you. Okay, and yeah.
Professor, if we simulate the historical data about one event.
Okay.
And the historical data make the prediction for the present.
Yes.
Okay. And compare this analysis and this conclusion with the observation of the present.
Yes.
If it is satisfied, can we use this model for predicting the future with low uncertainty?
Yes. On the other hand, you have to include in your statistical model, you have to take into account the possibility that the CO2 emissions increase. So basically, in your statistical model, you use a past pattern to predict the present, but the present is a concentration of CO2 that is 1.3, the original concentration in pre-industrial time, no, 1.5, I think. We are at least at 1.5. So we are at 1.5. In the future, you may predict with an emission scenario that the concentration will be 2 CO2. And therefore, in your statistical model, data-driven model, you have to find a way to take it into account. This is what I am introducing in this lecture. So in this slide, sorry. So if you use a traditional approach, a data-driven model, you have to find a way to account for future changes in climate, which and there are several ways of doing that. So let me just give two examples. The first one is a study that I think it's very relevant, has been presented by Australian researchers. Let me see what is the next slide. Yeah, okay, perfect. So let me present the study made by Australian researchers because I think it's very relevant. Their purpose was to estimate future extreme rain, okay, and in order to design some flood protection facilities. And let me just in the blackboard. So their purpose was to estimate future rain. Okay, so how can we do that? They first downloaded climate predictions, but they were not confident about that because if you are an engineer and you have some experience, you can gain a certain sensitivity. You see a prediction and say, okay, these models predict very different future values, for instance, or the prediction is really something that is not reliable. But basically, the discrepancy between models, indeed, the width of the envelope, the ensemble envelope, is an indicator. So they said, okay, we don't want to do that. And then what they did, and they were analyzing prediction of rain, okay, by climate models. What they did, they looked at the prediction, at the capability of climate models to predict temperature. And they were happier. We know that climate models are better in reproducing temperature than rainfall. And they checked it. They checked in the reproduction of historical data. The climate model was quite good in predicting the temperature. So they said, okay, let's take the climate model and then let's take a future prediction of temperature. Okay, I am at the forecast time T star. I want to make a prediction for the forecast time for the lead time T double star. This is temperature T. Okay, very good. I start from here and I get my climate model prediction, which is somewhere here. Okay, and here I get capital T double star. Very good. Now, what they did is, okay, now let's look at the data they were looking. And they took a past simulation, past simulation of, past observation of temperature, okay, and they got an increase, of course. And let's suppose that here we are at T star, and here I put time zero, but of course it's not zero because we have observations starting from 1850. Okay, okay, let me just put here 1850. Okay, and then look at the past observation of temperature. Like, let's suppose that every year you have an observation of temperature at a given location. Okay? And then they looked at the corresponding pattern of extreme rainfall. Okay, so this is T, and this is rainfall. And they looked at the progress of extreme rainfall. It's in a different scale. Okay, this is the scale of rainfall. Okay, this is the scale of rainfall T. So let me just put it here. Okay, and they got something like, maybe something like that, okay? And they observed that also extreme rainfall was increasing. And this is what we expect. So an engineer has to make an expectation before applying a model. Why we are expecting that? Because we expect that under global warming, extreme rainfall increases, okay? And they checked it and said, okay. And then they found a relationship a relationship to express estimated precipitation in the past here is expressed as a function of past temperature. Why did I put the hat here? Because this is an estimate, and it's not the observing one. And they estimate by comparison with the uncertainty. Okay, this is observed P, and then I get from here an estimate of uncertainty. Uncertainty of what? Of this relationship. Okay, of this relationship. Okay. Precipitation. Yeah, extreme precipitation. Okay. So they estimated such a relationship, which was non-linear, but they are not interested in the relationship. The important thing is that they estimated the relationship and the uncertainty of the relationship. So basically, then they went here, and based on the prediction, which we consider reliable. So let's forget about uncertainty of this prediction, because otherwise the graph becomes too complicated. This is a reliable prediction. They assume that in the future, the relationship between precipitation and uncertainty remains the same, and then in a different axis here, precipitation, they depicted the progress of future precipitation. And this was their prediction. And here they accounted for uncertainty. So this is the confidence band. You don't know still what is the confidence band, but let's assume. So what is the rationale? Is I take a data-driven model to estimate the relationship between precipitation and temperature. I get a prediction of precipitation of temperature through the climate model because I test that it's reliable. Why it's not reliable? Precipitation, and then I put the two things together. So I integrate the data-driven approach to the climate model, and I obtain a future prediction of precipitation. This is what they did. They made a design. So this is, I think, a good example of what I mean to say. What I mean to say is, when you make a prediction, there is an imperative. The imperative is you have two imperatives. One is you have to estimate uncertainty, and the second one is you have to use all the information available. So it's a mistake to drop a data-driven model, historical analysis, traditional approaches. It's a mistake to drop it. You have to integrate the information. And this is an example of how it can be integrated.
The estimation is based on the rainfall, global rainfall, or only in Australia?
No, they based it only for a specific location. Specific location. And what is the advantage here? The advantage is that you preserve the statistics of the process. If you use a data-driven model, I mean, what you know about the past patterns is used in making the future prediction. You use it. So you are indeed satisfying the second imperative, use all the information. Now you may ask me, so in general, how can we do? Because this is just an example. In general, you have to use all the information available, and based on the information available and your perception of its reliability, you have to conceive ad hoc solutions by profiting from the examples. Usually when I propose at the national level to use this kind of approach, people tend to say, can we do better? Why? Because it looks like something a bit too simplified. Okay, so to assume that there is a relationship between extreme rainfall and precipitation looks like something that is too simplified. But In principle, I would say that it's a very good starting point. So basically, what is a way to generalize the concept? Try to understand when a climate model is good. Okay, in simulating temperature, usually it is good. But it may also be good in simulating precipitation at large scale or at the annual scale. So annual precipitation may be simulated in a good way by the climate models. Usually extreme precipitation is not well simulated. When you go in the tail of the probability distribution, extreme means you go into the tail, uncertainty becomes larger. So simulating the average is relatively easy. Predicting the average is relatively easy. If I toss a coin and I have to predict what is the average, it's very easy. The average is 0.5, is in between head and tail. But if I have to predict the extreme, like what is the chance that I have of getting 3 tails in a row, this becomes very challenging. So basically, try to understand what are the predictions delivered by climate models that are good. So it may be annual rainfall, it may be temperature, it may be the standard deviation. The average is generally good, and what about the standard deviation may be good. And then you use these good predictions by the climate model to adapt your data-driven model. And here in the slides, I just talk about, sorry, it's not the presentation, this one. I'm talking about, sorry, stochastic models, means statistical. And it's not only stochastic model, not only statistical models, there are data-driven, as I said. I still think that, statistics is very good because it has a solid theory behind it. But indeed, I recognize the power of data-driven models. They are very fast. They are very, they are a very nice tool. So don't drop them. And it's not true that engineering has to be revolutionized because of climate change. It's not true that the traditional methods are no more good. It's not true that probability distribution are no more representative of the future. It's absolutely. I mean, we may need to adapt them, but they are still representative. How can they not to be? I mean, if they are representative of the past, the same physical process, the same context, the same, in the future, something may change, but not everything doesn't become completely different. Okay, that's it. And I think that now I may give you a more practical example by using a model that you well know of how can we make a prediction of future climate with a data-driven model. And the example that you well know is linear regression, extrapolation of a linear regression. So this is very widely used in engineering, actually. So it is quite common that in climate science, it's quite common that in order to understand climate change, we fit a trend line. And the trend line very often is linear, not non-linear, because of the reduced uncertainty. And I hope that you get this. If you estimate a non-linear trend, the uncertainty is much larger than estimating a linear trend. This is why the linear trend is often used. I hope that you get it, and you may try. And it's very easy to make trials of extrapolation. You can generate a synthetic series of data, and then you split the data into chunks, and you try to make predictions with a trend line or with a nonlinear extrapolation. You can make an exercise on that. Anyway, let me just pin the blackboard. So what does it mean, what I just said? what does it mean? Fitting data with the trend line. So let's suppose that make an example of temperature because it's very common. So temperature T, and this is time. And let's start from 1950 to 20. These are almost 200 years, so I should get here. This is 2025. And this is second T is here. And this is 2100. Okay. So it is, if you look at the progress of global temperature, and usually we get something like this. The red is gone. Global temperature, as you know, is something like this with some deepening, increase of the slope, increase of the trend in the recent past. Okay, usually if I just want to make a sketch, it's this one, and then here 2015, and it is very easy to estimate here a trend line, and it is something like this. This should be straight, okay? And because it's linear regression, we define linearity as a straight line. So this is possibility, very easy to begin. We will get into the mathematical details of the linear regression, which you already know, but to give you an example, in the next couple of hours, we will get into the mathematical details. Why I want to get into the mathematical details? Because it is interesting to estimate the uncertainty of this trend line. And the uncertainty here, we can easily estimate it by, as I said, comparing the trend line with the observations. But anyway, let's forget about it for now. And there is a widely used approach to say, okay, if I want to make a prediction in 2100, what I can do is to extrapolate the trend line and get the prediction here. This is a possibility. And then, of course, if you talk with a climate scientist would say, this is not good because if you estimate the trend line, for instance, by forgetting the first part, but only on the recent past, you get a slope like this. You get a trend line like this. And therefore, if I extrapolate, I get here, which is a prediction that would look more convenient to a climate scientist, because the climate scientists, they by nature tend to be very conservative. Okay? And therefore, the climate scientist would say, so where do you fit your trend line? And my reply would be, depending on where you fit it, you get an estimate of uncertainty. Let's also compare the uncertainties, okay? Because, but indeed it is true that this interpolation relies on very heavy assumption, linearity. So if I estimate here a nonlinear curve, then I would get closer to this prediction. So, I mean, this is another example where the assumptions in a way condition our estimation, and therefore it's but it is a possibility. I was saying, therefore it's important to evaluate the underlying assumption, whatever prediction I make. But the topic of linear regression of climatic data is very important, because usually this is the way past climate change is analyzed, by reporting the trend. And for instance, when I said sea level rise was from 1850 about 1.5 millimeters per year, this is valid under the assumption that is linear. And actually sea level rise is really well fitted by a straight line. But if I look at the temperature, it's not really linear. But in any case, I mean, to estimate past changes, it's a method that is widely used. To make predictions, it's not widely used. But let's just now try to get into more details about linear trend estimation. And in order to do that, I have to change the link and move to the next one. Let me just see if there is something in the lecture that I don't know. I think these are further specification, but okay. Let me just see one thing. Forget about from section 7. Forget from here to the following, because it's an introduction to decision theory, and therefore this is the subject of the next lecture and will be covered by another link. So forget about section 7, and forget doesn't mean that it's wrong. If you read it, it's no problem, but it's something that I'm not teaching now, okay? Let me go back, and now let's, and another thing, I will give a different color with explanation to what I skipped, but I still want to keep here, okay, for your information. Like, for instance, climate change and water, I'm skipping it. And, but it is a nice reading, in my opinion, and it's by far the most read page on my website, and it's very easy to read, but we are not focusing explicitly on it because it's too narrative and not very technical. We need to move forward to something more technical. So I will give to this link a different color. And so far, I think we did all of them. Climate models, we just concluded. And then there is risk-based, we already discussed it. And climate change and water, I'm skipping. And then we go here, inductive and deductive estimation of climate change and climate impact. We will also skip model calibration and validation. Okay, here I don't have the PowerPoint, and therefore let me just introduce this lecture, because before moving into linear regression, I need to make an introduction about the general purpose of this lecture. And the general purpose is indeed how to obtain predictions, and predictions not just of climate change, but also impact predictions. Okay, and the impact, how can we define impact? We can define impact as, I wouldn't introduce a rigorous definition. I would say that impact can be estimated through the damage. Why I wouldn't say, I wouldn't introduce a rigorous definition? Because I want to remain in a general context. The impact can be estimated as economic damage, or can be estimated in loss of lives. And I wouldn't use a rigorous definition, because I would prefer to keep it very general, because depending on our design project, depending on the consequences that climate change may have, impact may be measured with different approaches. And I would prefer to just say that the impact is a measure of the damage that we get from climate change, or yeah, damage is fine, but not limited to economic damage. So estimating the impact is a first step to design a climate change adaptation action. Okay, so basically I get an estimate of climate change, and now we know how to get the estimate. Okay, we have to say something more about linear regression, but basically we know that we can use climate models, we can use data-driven approaches, we can integrate both of them. So we get a prediction of future climate, and then I need, through an impact model, through an additional model, I have to understand what is the consequence on the human society. And then from this consequence, I get the project variables, okay? And so we know that impact can be measured by estimating risk. And it's a possibility to measure impact. We know that risk usually refers to an economic damage, but can refer also to the number of lives. So risk is indeed a good way to estimate the impact, because it measures indeed the damage that I get from a given climate extreme that is changed, and we know how to measure risk. It's probability, vulnerability, exposure. We can work under the assumption here that climate change has an effect on the probability and doesn't have a direct effect on vulnerability and exposure. We already said that actually there might be an indirect effect, because people, after an increase of the hazard, after an increase of the probability of an extreme, may react by adjusting vulnerability, but this is an indirect effect. Okay, so now let's assume that climate has only the most important effect on the three terms, on the three factors. And the most important is the fact that climate changes the probability. Okay, climate change changes the probability. I think I already mentioned to you that you will find different definitions for these three factors. So some people, for instance, in some papers, scientific papers, you may find that if I build a levee, to give you a practical example, I also reduce probability, because these people define the hazard in a different way. So let's keep our original definition. The hazard is the probability of getting an extreme, not of getting the consequences of the extreme. So the hazard is not the probability that I am flooded. The hazard, because the probability that I am flooded depends on the river flow, but also on the levee, on the presence of the levee. The hazard is the probability that a given climatic extreme occurs. Okay? So if we take our original definition for hazard, vulnerability, and exposure, we can safely say that climate change has only an effect on the term P, on the factor P. Okay, so we already discussed that the future P, the future probability, can be estimated with different approaches. And we talked in particular about data-driven and climate models. Actually, we can highlight this difference also saying that we can make a classification between deductive and inductive approaches. Data-driven is inductive. It means that I look at what happened and I inductively estimate what has changed. Deductive means that I start from the theory, I start from the forcing, and I deduce the change through a model. Okay, just I want to make sure that you know the terminology, because sometimes what I call physical models, climate models, process-based models, I also used this definition. They are called, these approaches, also deductive approaches. When you use a model, usually it's deductive. While inductive, as I said, you look at a disaster and you look at a flood, the flood occurred, and then you look back at what has changed.
So the agreement is deductive.
Yes.
Physical model is deductive.
Esatto, exactly. Okay. Okay, so, and here I will introduce, but we go in the afternoon, a linear regression trend analysis as another example of inductive estimation, data-driven. Okay, and it is particularly useful that I give more details on linear regression because it allows me to give also more details on uncertainty, because it's very easy to estimate uncertainty in a correct way for linear regression, which is based on the comparison with the past observations. It is very easy to demonstrate and therefore to introduce the theory of uncertainty in linear regression. And you will understand by comparison that the ensemble is not a good prediction. I mean, it's a different prediction of uncertainty.
Deductive will be from general to particular, and inductive will be from particular to general.
Yeah, I wouldn't say from general to particular because I mean, I would prefer to say deductive is from the data to the conclusions, and this is inductive. Deductive is from a model to the conclusions. Because general particular usually refers to large scale or local scale, and it's not really the case here. The climate models and the data-driven models are not different in terms of scale. Okay? They are different in terms of conceptual approach. The data-driven looks at the data and goes back to the change, and therefore it's inductive. Physical model, climate models, look at the inputs and through the theory goes forward to the change. Okay, okay, good. So let's meet at 2 p.m.